All right, it's time for some probability here. Again, this is going to be the common thread lecture for prob and stats and also theory of probability. Now, there are some details that I will go into a lot more detail concerning for the theory of probability folks. So those people can stay tuned for that. One thing that I am actually thinking about doing, because I know that some of you have had issues with the streaming because the videos are so huge. I think that's probably an issue across the board. I'm working on making a YouTube channel. I don't know when that will actually come about. I don't know what I'm doing with any of that. I've been reading some stuff. So I'm hoping that within a couple of days I can sort that out and figure out what it is I'm going to do about that. That way you should be able to watch the videos in YouTube itself, and they are the experts at streaming quality and whatnot. So I don't think that you would have the same kinds of issues if that indeed does describe your situation. Okay, so I'm going to try to pull that off. So just bear with me. And actually, for the prob and stats people, this might end up being a fairly shorter than usual lecture for that reason. And I'm trying to, do that so that you'll have that to your advantage. And that's just taking up a little bit more time. Okay, so what I want to do is talk about a few, let me share this with you. Talk about a few specific kinds of distributions, okay? And before we do that, I want to, for once and for all, describe what the expected value or the mean value is for a continuous random variable. Now remember, when we had a discrete random variable, we added up, it was like a sum of over all possible x values, x times p of x, where p of x was the probability mass function. Do you see the parallels of this definition here? The expected value of x is going to be the integral over all possible values, negative infinity to infinity, x times the density at x dx. Okay, so the density or the probability density function is weighting, W-E-I-G-H-T-I-N-G, weighting the x values properly. Okay, so like if f of x has a larger value, it's going to weight those x values more heavily. And that's kind of what was happening before in the discrete case. P of x big would put more weight on the x value in the expected value. Okay. Oops. And what about this? If x is a continuous random variable with probability density function f of x, and h of x is any function of the random variable, so it might be x squared or 5x squared minus 3x plus 2 or something, that might be what h of x is, then the expected value of h of x, denoted by e of h of x, or mu sub h of x, is just, replace x with h of x. Okay, so h evaluated at some value x between minus infinity and infinity is weighted by the density value there. So that's the expected value of h of x. It's just the expected value of x is a special case of this more general formula down here where h of x is just x. Okay, so this ought not be too surprising, hopefully. So yeah, okay, moving on. Variance. So what is the variance? The variance of a continuous random variable with probability density function f of x. You either denote it by v of x or var of x or sigma squared or sigma sub x squared if you want to talk about x. And that's just going to be the expected value of this thing. And because, remember before when we actually showed why it was that, you know, when we multiply this out, we can use the linearity of expectation, and we got a nicer formula for the variance. Well, the linearity of expectation is still true because the expected value is still defined in terms of integrals as opposed to sums. And remember, with integrals, you can always break it up across a sum or a difference. You can pull out constants. So the linearity of expectation still holds. You can break it up over sums and pull out constants. All those sorts of things are still true, even in the continuous case. So just like we did before in the discrete case, when you multiply out this square, you get the same formula we had in the discrete case. Okay, and incidentally, mu in here is just the expected value of x. And again, the variance is giving us a sense of how far on average the random variable x is deviating from the mean. Okay, so you measure an x value against what the mean is, you square that so that that difference is positive, and you take the average value of that. And that's going to tell you how far on average x is tending to deviate away from the mean. And of course, just like was the case in the discrete situation, the units here, if x is like in dollars or something like that, then the variance has squared units, okay? And so a lot of times when we don't want that, we want the original units, but to do that, we would have to take the square root of the variance, which is what we call the standard deviation, okay? And that's what this is right here, okay? So what about this? Let x be a continuous random variable with probability density function given by that, okay? So 3 over x to the 4th for x greater than 1 and 0 for x less than or equal to 1, okay? So that's interesting, okay? So one thing I will point out is, technically speaking, we should check to make sure that this thing actually is a density, but let's just kind of take that for granted here, okay? So that is, if I were to integrate this thing, okay, first of all, before 1, you don't have anything. But if I were to integrate this thing for x bigger than 1, I should get what? I should get 1, okay? And I don't know, I guess, all right. You talked me into it here, so let's see. Let's go ahead and do that. It should be fairly easy to do. I'm gonna do it right in here. So that would mean that the integral from 1 to infinity, this had better be 1. The integral from 1 to infinity of 3 over x to the 4th, 3 over x to the 4th dx, okay? What's that equal to? Well, okay, this guy right here is 3x to the negative 4. Yeah, that's what that is. So when I do the antiderivative, I'm going to have to go, I'm going to have to add 1 to the power. So I'm going to have -3, and I need to divide by -3. So I'm telling you the antiderivative of this thing is -1 over x cubed. -1 over x cubed. And that's evaluated between 1 and infinity. Okay? So what is that? Well, all right. What is that? Well, okay, look. If I let x go to infinity, that's like what plugging in infinity means. This is basically 0. Yeah, this is like 0. And on the other hand, I go minus negative, which is plus 1 over 1. So yeah, that's just 1, which is exactly as it should be. See what I mean? So that's amazing. So, and what about the expected value of this random variable? Let's do that too. Okay, let's do the expected value of x. Okay, how would I pull that off? Okay, well, that's equal to the integral from 1 to infinity of, okay, I need to multiply x by this thing. If I multiply, it's going to be x times f of x, right? So that's going to be 3 over x cubed, 3 over x cubed, because a factor of x cancels, dx. And again, this is 3x to the negative 3, 3x to the negative 3, that's what this is, right? So that's 3x to the negative 3, yes? And if I do the antiderivative of that, I would have to add 1 to the power, hence giving me negative 2, and I would have to divide by negative 2. So this is going to be, you know, negative 3 over 2 times 1 over x squared. Okay, and I'm evaluating this between 1 and infinity. Okay, so what is that? Well, that is equal to, what do I get? Well, if I let x go to infinity, this thing goes to 0. Minus negative, which is plus, this thing evaluated at 1, I get 3 over 2. Okay, so that's what the expected value of x is. Okay, that is mu of x, mu sub x. Okay, finally, what would happen if I wanted the expectation of x squared? Okay, so what would the expectation of x squared be? Well, all right, expectation of x squared, what is it? What is it? Well, it's going to be the integral from 1 to infinity, and I would have to multiply the density by x squared. So this would be 3 over x squared. 3 over x squared. Okay, dx. Okay, interesting. Okay, and just as before, okay, it's like going to be 3 times x to the minus 2. You add 1 to the power negative 2, which is negative 1. So this thing is going to end up being, you know, negative 3 over x. I'm telling you. Okay, so negative 3 over x. Okay, because, you know, if I add 1 to the power negative 2, I just get negative 1. So this time I'm just dividing by negative 1. This is evaluated between 1 and infinity. Okay, and just like before, the infinity part goes to 0 minus negative, which is plus 3. Okay. So what is the standard deviation here? Sigma sub x. Well, it's going to be the square root of the expectation of x squared, which is 3, minus the square of the expectation, which is 3 minus 9/4. Okay, whatever that is. Yeah, so that is sigma sub x on this thing. Okay, so let me go back to the other screen now. Just wanted to, you know, I said I wasn't going to go into all kinds of detail. I ended up going into all kinds of detail, so that's all right. Okay, so I'm here again. We did this thing. This thing was indeed a density, and we computed these two things. This guy ended up being 3/2, and the standard deviation ended up being the square root of the quantity 3 minus 9/4. Okay, so let's talk about some specific distributions. Okay, some specific distributions, and I don't know if we're going to get through them all. But I will say that probably the most important of these three is the exponential. Particularly for those who are interested in actuarial science, the exponential distribution comes up all over the place. It is just ubiquitous, okay? And I'll talk about why in a couple of minutes here. So here is the exponential distribution, okay? So a continuous random variable x is said to have an exponential distribution with parameter lambda greater than 0 if the probability density function of x is given by that. Okay, so lambda, that ought to remind you of something. And yeah, it really should. That lambda right there, it's not an accident that the letter lambda is being used there. It's because the exponential distribution comes up when considering the so-called Poisson process, which was the last distribution we studied in the discrete case. Okay, I'm not going to go through the details of why this integrates to 1. It's fairly straightforward to see why. The main thing is the antiderivative of this guy is just negative e to the negative lambda x. And then you have to plug in infinity and 0. When you plug in infinity, you get 0. And then you plug in 0, you get 1. So it integrates to 1. So that's the exponential distribution. It looks like this. And I am telling you, this is the distribution that comes up when you look for, in a Poisson process with parameter lambda, when you look for the first occurrence, the first observation of a Poisson process with parameter lambda is going to have the exponential distribution with parameter lambda. Okay, so let me say that again. If you're observing a Poisson process with parameter lambda, then the amount of time you have to wait until the first occurrence or observation in that Poisson process will have the exponential distribution with parameter lambda. Okay, so that's where the exponential distribution comes up in practice quite a bit. And you could see why in actuarial science, where you're obsessed with the number of bad events that happen, like when you're trying to discern what to charge someone for their car insurance, for instance. So you could see why me wanting to know the amount of time that goes by before the first occurrence would be highly interesting to an actuarial scientist. Okay, that definition ought to remind you a little bit of the geometric distribution. The geometric distribution, we were doing some experiment over and over and over again, and we were waiting for the first success, and the number of trials until the first success was the geometric distribution. That was an integer value, yeah? Here we have a continuous random variable that is measuring the amount of time until the first occurrence in a Poisson process, and that has the exponential distribution. Here's a couple pictures of various distribution curves right here. So yeah. Here are some little factoids, okay? Cumulative, and again, I'm gonna go into a little bit more detail for this with the theory of probability folks, because they, they're obsessed, right? They want to know all the details. But in general, I mean, you could just, if you want, you just believe these things, yes? So in the prob and stats people, you can just say, yeah, all right. That makes, I believe it. So here is the cumulative distribution function. It's right here. And the way you would get that is just by integrating the density. Okay, integrate the density from 0 up to x, and you'll end up getting this. The expected value is 1 over lambda. What? The expected value is 1 over lambda. Well, that makes sense. So suppose suppose I tell you, okay, so let's think about this. Let's just talk about this intuitively. Suppose I tell you that in a 1 hour period of time, I expect to see 2 cars pass. 2 cars will pass, okay? In a 1 hour period of time, I expect to see 2 cars pass me by. Well, okay, so the number of observations during that hour is going to have the Poisson distribution with parameter lambda equal to 2. Lambda equal to 2, okay? And I told you that the exponential distribution is the time that goes by before the first observation. Well, if I expect to see 2 observations in 1 hour, how long do you expect to have to wait to see the first car? 1/2 hours, half an hour. 1/2 hours, which is half an hour. And that's exactly what that expectation formula says. Okay? And so, and believe me, so the moment generating function, by the way, the moment generating function is computed in a way similar to what we did in the discrete case. Let me just go over here and kind of write down the definition of the moment generating function. So go on the whiteboard, the generic whiteboard. I'm going to clear the whole thing. Clear all drawings. Okay, so let's see. So the moment generating function of t is just the expected value of e to the tx, okay, which by the way is going to be the integral from -infinity to infinity, e to the t little x, little x, okay, times f, the density at x dx, okay? So it's defined just in a way similar to what we did for the discrete case, right? So before we were like adding up all the x values, e to the tx, p of x, where p of x was the probability mass function. But here we use the density to give us our moment generating function. Okay, so let me go back into our presentation over here. Okay, so that's how the moment generating function is computed, and you end up getting this. And if you believe that this is the moment generating function, then it's just a short step to show that the expectation and the variance are these things, because you can still take the derivative. You can still take the derivative of the moment generating function twice, plug 0 into the second derivative, and subtract off the first derivative evaluated at 0 squared, and that will give you the variance. All right. So let's see here. Data collection at a certain airport suggests, there's a typo there, but that an exponential distribution with mean value 2.725 hours is a good model for rainfall duration. Okay, exponential distribution with mean value 2.725 hours is a good model for rainfall distribution. Okay. What is the probability that rainfall duration is less than the mean value by more than half of the standard deviation? Okay, so the mean value here is 2.725. Okay, if the mean is equal to that, you know that the mean is equal to 1 over lambda. Okay, so let me go over here into the board mode here. I don't know, for some reason I'm into doing this right now. I'm trying to perfect my drawing skills with this little whiteboard, okay? So I have a mean value, okay? So I have a mean value of 2.725. 2.725. okay? And that is equal to the expected value of x, but you know that that's also 1 over lambda. Okay, so that means that lambda is equal to 1 over that, 1 over 2.725. Okay. What is the probability that rainfall duration is less than the mean value by more than half a standard deviation? Is less than the mean value by more than half the standard deviation. So that means that it's not just below the mean, but it's actually to the left of it by half a standard deviation. Okay, so I want the probability that x, and remember, I'm not too concerned about being equal, right? That doesn't make any difference for a continuous random variable. That x is less than the mean, which is this, okay? So the mean is 2.725. Okay. Minus, now the variance, remember the variance is 1 over, is this thing squared, okay? And we want to be below the mean by more than half a standard deviation. So 2.725 minus half of what? Half a standard deviation, okay? Well, the variance is 1 over lambda, or the variance is 1 over lambda squared, rather, okay? So just to remind you of that, you know, look at this thing over here, right? So the variance is 1 over lambda squared. So the standard deviation is just 1 over lambda again. The standard deviation is 1 over lambda. The standard deviation is 1 over lambda again. Okay, sorry, I was talking and I wasn't. So like, look at this, the variance is 1 over lambda squared. The standard deviation is 1 over lambda, okay? So going back over to, the whiteboard itself again, okay? So it's half of the standard deviation, right? Below this by half the standard deviation. So that'd be half 2.725, okay? Because actually the standard deviation is the same as the mean. That's amazing. So overall, you guys realize that this is actually half of 2.725, right? It's just half of 2.725 again. 2.725 again. Okay, and how do I compute that? Well, guess what? I can use Excel. Okay, so let me go over here and get out of this, and we'll open up Excel and we'll look at this together. Okay. If you ever change your mind, all right, well, I don't want to change my mind. Okay, so this is equal to, so x is more than 1/2 a standard deviation below its mean. That means x is less than half of 2.725. So it seems like I would want to do the exponential distribution, okay? X, so what's my x value? Well, I'll have it computed, but it was 2.725 divided by 2, basically, half of that, okay? And what is my, what's my lambda? Okay, what's my lambda here? Well, so what is lambda? Remember, lambda was 1 over 2.725. You got to be careful about that, yeah? And cumulative, yes. Okay, yes, it is cumulative. Okay, so it's 0.393469. I guess that kind of makes sense because, you know, you usually think about the mean as being somewhere in the middle, basically. And now I'm asking for the probability that I'm more than half a standard deviation to the left of the mean. So, you know, it makes sense that it would kind of be something like that. Okay. All right. Let's go back to the presentation. Okay. So, yeah. So this is an important feature of the exponential random variable. Exponential random variables have something called the memoryless property, which basically means that if I know that x is already beyond some specific number t0, then the probability that I'm going to be beyond t plus that t sub 0 is it's not really changed. It doesn't really change from, because look, I mean, how far have I gone if I go from t0 up to t? Well, I've gone t units. And basically, this thing has kind of forgotten about the fact that it's already had to wait t0 units. To get to t, beyond t0, it's just like waiting t units, period. Okay? So this paragraph down here, this means that if x equals the length of time that an object lasts, and x has an exponential distribution, then the probability that the object will last at least t more years is not affected by the age of the object. Okay, so the knowledge that it's, you know, that it's already been there for some amount of time doesn't affect, you know, it doesn't affect the probability that I'm gonna have to wait some amount of time beyond that. That's the memoryless property, and that's easily verified using the cumulative distribution function. Okay, this thing is easily verified using that. Okay, it's called the memoryless property of the exponential random variable. Okay, given that the rainfall has lasted 2 days, what is the probability that the rainfall duration will be at least 5 days? Okay, 5 days. Days? What in the world? Let me see something here. Okay. Well, okay, so I mean, I have hours in here, but, and now we're talking about days, but okay, whatever. Okay, days can be converted to hours, no problem. Okay, so let's think about that together. Given that the rainfall has lasted 2 days, what is the probability that the rainfall will be at least 5 days, or that the rainfall duration will be at least 5 days? Okay, and that's not too hard to do. So let me go back in here, or let me go in here. Okay. Okay, so I had this from before. Yeah, I was computing this. Let's clear it. And I want to, given that the rainfall has lasted 2 days, so I want the probability given, all right, so I'm given that the rainfall has lasted more than 2 days. I want to know what's 2 days, okay? Let me clear this, your drawings. So I want the probability that, so I'm given that x 2 days, okay, how many hours is 2 days? That's 40, or has lasted 48 hours. Okay, so x is the rainfall duration, 2 days since we were doing things in terms of hours here, okay? So it's 48 hours. What is the probability that it will be, that there will be at least 5 days of rainfall, okay? So what's the probability that x is greater than, okay, what's 5 times 24? Okay, it's 120, yeah, 120. Okay, so x is greater than 120. Okay, well, the point is the knowledge that it's you know, lasted 48 days or 48 hours. What's the probability it's going to last 120 hours? Well, it's almost like it's as if you've kind of started the clock over at 48, right? So this is going to be the probability that X is greater than, what you would do is you would take 120 and you would subtract 48, which is 72, okay? 72. And how would you compute that? Well, that would just be 1 minus the probability, 1 minus the probability that X is less than or equal to, or actually here you can just say less than 72. X is less than 72. So you could use Excel to actually pull that off for sure, okay? Go 1 minus, and you would do the cumulative distribution function up to 72, okay? So let's go back in here, okay? That's how you would do that. I'm going to just introduce the gamma random variable, but the first thing that we have to know about is this thing called the gamma function. And I will say the gamma random variable is related to the exponential in that basically in the exponential, if we have the Poisson process, the exponential is the amount of time it takes to get to the first observation. And the gamma random variable is an extension of that. The gamma random variable is basically saying, I want to wait till the second observation. Again, this would be something that would be important for, for actuarial scientists, people that are setting, premium, what to charge you for your premiums for insurance and whatnot. That would be, okay, if I said I want to wait for the second observation, that would be like the gamma random variable with parameter 2. And you would also have to tell, like, what lambda is, of course, kind of like what we had to do for the exponential. Okay, so the gamma and the exponential are related in that you're waiting to observe some number of occurrences, whereas the exponential, you were waiting to see the first occurrence. So the gamma is to the exponential as the negative binomial was to the geometric. Let me say that again. The gamma is to the exponential as the negative binomial is to the geometric. But one thing that comes up in here is something called the gamma function. This is where this random variable gets its name. The gamma function is defined by this crazy integral right here. And in order to mess with this and to prove properties of this, you would have to do stuff like integrate by parts, which gets a little bit annoying. But this is the gamma function. Gamma of some number alpha, this is a capital gamma, Greek letter gamma, and of alpha is equal to this crazy integral right here. So alpha has to be greater than 0. This function has the following properties. If you plug in a positive integer, that's what this means, right? Or positive integers, you end up getting n minus 1 factorial. So the gamma function is really like the factorial function, except that it's just off by 1. So in some sense, the gamma function is an extension of the factorial function to things that aren't necessarily integers. So I could even talk about things like pi factorial in some sense by using the gamma function. Okay, pi factorial would basically be like gamma of pi plus 1. Okay, it has this property that gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1 for alpha bigger than 1. That's where this factorial property comes from. The way you prove this is by using integration by parts. And one of the most important values is the gamma function at 1/2. That equals the square root of pi. So you get a special integral in here. You get the square root of pi. It turns out that's going to be related to something we'll study later on called the normal distribution. Okay, so here's the gamma function. I described, at least in principle, what the gamma distribution is. Okay, and I think that I'll at least show it to you here, and then we'll call it a day for now. So here are some basic facts about the gamma random variable. And again, I already told you that you should think about the gamma as extending the exponential random variable. You're basically waiting to observe some number of occurrences. Okay? So some number of occurrences in a Poisson process. A continuous random variable x is said to have a gamma distribution if the probability density function of x is given by that. Okay, look at that. Look at that obnoxious thing. It's crazy, right? So one thing that I would point out is if you take alpha to be 1, if you take alpha to be 1, then you basically have something that looks like the density of the exponential random variable, except you have this one, you have the 1 over beta thing sitting there. So essentially, if you take lambda to be 1 over beta, and you take alpha to be 1, you will get the exponential random variable. So what alpha is for the gamma random variable, alpha is basically the number of occurrences you're waiting for. Alpha is the number of occurrences that you're waiting for. And 1 over beta, which is lambda, is the number of observations you expect in the period of time you're observing, yes? So, you know, and again, remember the expected value of the exponential random variable is 1 over lambda, okay? So beta is equal to 1 over lambda. And said another way, lambda is equal to 1 over beta. So is it any surprise that the expected value is just, we're waiting for the alpha observation, that it's alpha times 1 over lambda, basically, or alpha beta, okay? So beta is 1 over lambda, if you want to think about it in the Poisson case. And is it any surprise that the variance is alpha times as large? Like here's beta squared. Beta is equal to 1 over lambda, and 1 over lambda squared is what we got for the exponential. It's alpha times as large. And I am telling you, this moment generating function is exactly the same as what we had back here. Like 1 over 1 minus t over lambda. 1 over lambda is basically beta. So 1 over 1 minus beta t. Let's see, is that what this would be? 1 over 1 minus beta t, and it's raised to the alpha, because you don't just wait for one observation, you wait for alpha of them. It's like you just kind of start the process over after each one of those observations. You wait for the alphth observation. So again, the gamma is to the exponential as the negative binomial was to the geometric. And the gamma and exponential are tightly connected with this whole Poisson process. That, my friends, is important, okay? I think just, I don't know if I'm gonna go into the details yet. Yeah, I think I might skip over, I might not do any more than what we've done right here for now. I might take a little bit deeper of a dive with the theory of probability people on some of this stuff, but I think that this is enough for now. We'll do some examples next time with the gamma, and I'll introduce the chi-square, and then we'll be getting pretty close to the normal distribution. That is all for now. Bye.